We want to welcome everyone here that's joining us today for Dry Scrubber Users Association's May 2021 webinar session. I'm your host and your DSUA president, Jerry Hunt. For those of you that are familiar with us, welcome back. Thanks for coming back. For you that are anyone that's listening for the first time or joining us for the first time and not familiar with Dry Scrubber Users Association or DSUA, it's a nonprofit organization. It's been around in the industry here in the US since 2008, and the whole intention and purpose and goals of DSUA is essentially promoting innovation and evolution of all the dry scrubbing solutions. So if you've got a spray dry absorber or a circulating dry scrubber or DSI system and having problems or looking to optimize, this is the forum for you. DSUA also becomes a platform for you guys to be able to have resources, to collaborate, to network essentially, and try to reach out to others in the industry with similar technologies. The webinars essentially have evolved because of the global pandemic. Historically, DSUA, we would do an annual in-person conference here in the United States, but because of the global pandemic, essentially, we've kind of pivoted over to a webinar format that we do on a monthly basis. And we've been doing it since last year, and we're going to continue through 2021. And as some of you may have seen in some of the announcements in the past, that we're not going to do an in-person conference this year officially as we have in years past. So hopefully 2022 will resume as normal. So till then, please continue to tune into these webinars and check out the recordings that are going to be posted on the website. Today, you're going to hear presentations from Matthew Wilson and James MannII of TVA about how they're utilizing drone technology for internal inspections of scrubbers and silos and such at their facilities, as well as a presentation from Guisu and Sean Dooley of Reaction Analytic Solution and Nol-Tec respectively. And they're going to be talking about the use of computational fluid dynamic modeling and how it's been utilized to optimize DSI performance. As I said before, if you got to hop off or you want to share this in the future, this shortly after, we'll get this recording posted and it'll be up on the website and shared through the LinkedIn page. So if you've got to hop off or again, you want to share this, stay tuned. This will be up on YouTube and it'll be free public access for others to view in the future. As far as any questions, you guys should know that see there's a Q&A function. So please submit any questions you may have, questions, comments, and both myself and the moderator will be sure to make sure that they get answered to the best of our ability. Otherwise, just stay tuned to the DSUA website, follow the LinkedIn page. If you're not on the mailing list, send us an email through the website just to stay connected to what's going on. But first and foremost, we want to thank our sponsors, and I'm going to share my screen. So bear with me here, because we certainly can't do this without our sponsors, as well as, the sponsors that you're going to hear about today. As far as DSUA and the support, these are folks that are highly involved in all the DSUA industry and some, whether it's a consumable or a piece of equipment or some kind of service. These are folks that if you're looking for a solution to address a problem, these sponsors are folks that may be the first good resource to start with. So our first sponsor is going to be Mississippi Lime Company. They're a world-class producer of calcium-based products. So quick lime, hydrated lime, calcium carbonate. They've got over a century of producing these products from one of the richest limestone reserves in the world. So, and they're supplying products not only through North America, but as well as across the globe through over a dozen plants and terminals. And one of the members of Kurt Bean from Mississippi Lime, he's one of the DSUA board members that's been working with us and supporting us, as well as Mississippi Lime. If you're looking for more information on them, they March 2021, they gave a DSUA webinar about enhanced hydrated lime fundamentals. So some good stuff there. And certainly if you guys are looking to talk to someone from Mississippi Lime, Kurt Bean would be your guy, and we're happy to facilitate and put you in touch with that. Integrated Global Solutions, IGS. They're an international provider of surface protection and material handling solutions. They've got over 30 years of experience helping customers solve whether it's metal wastage, ash accumulation, or just general reliability problems in mission critical equipment. They're an industry leader, and the development and application of these solutions. So if you got something corrosion or erosion related and it's in a challenging environment, IGS is someone that you guys want to reach out to and connect to help address some of these problems and find a solution. Leckler is another one of our sponsors. They've got over 140 years of experience designing and manufacturing spray solutions for air quality control systems. So if your needs are going to be anything from whether you need a nozzle or a nozzle lance, valve stand, mist eliminator, whether it's a gas cooling purification or some kind of emission control, whether it's SO2 or NOx, Leckler has something for you there. You might want to reach out to them. They also have technical expertise to advise, end users with custom solutions to meet compliance needs. So their experts understand all these spray technology solutions, and they're happy to share their support and knowledge to help you guys develop a partnership towards developing solutions. So you can hear more about it again, March 2021 of this year. Stuart McKenzie, who is also one of the advisors of DSUA, he gave a presentation along with Jacksonville Electric Authority about SDA optimization. So you can learn more from those guys if you want to check out that webinar. And Gecko Robotics, they're a revolutionary robotic technology for industrial infrastructure inspection. So they've got wall climbing robots that can do internal inspections, as well as they have a team that helps execute these NDT inspections, and they've got global clientele. So their robotic technology has the ability to execute these routine inspections and compile comprehensive data with high speeds, and also, most importantly, able to do it safely in hazardous environments. So again, these guys also gave a presentation at one of our webinars back in February of this year from Michael Paul Jenkins. So if you're interested to learn more, please check out that webinar on the website. They've been an avid supporter of DSUA this year as well as last, in terms of Sam and Amanda at Gecko have helped us with this platform, which has been much appreciated. And Dave Kahn from Gecko is he's still affiliated and works as a supporter to the board, and former VP and well-versed in DSUA and what the board executes. So thanks again for the support and the sponsorship. And Redicam, they provide an extended range of equipment for flue gas treatment, air pollution control solutions across many industries beyond not just the coal-fired power applications, but other industrial applications. And they serve end users with these technologies able to meet stringent acid gas emission requirements in a cost-effective manner. And they've got over 4 decades of operating experience, so they've got a wealth of knowledge to help you guys navigate through custom problems to develop custom solutions. So whether you've got a greenfield site or you're looking to retrofit a solution, they can help you guys get to your objective. So also from Redicam, Salvatore Gallo has been an advisor to the board and volunteered his time to kind of help us as well. So wanted to acknowledge those sponsors and again, thank them for all their support, and as well for the webinar, DSUA, and all their support in the industry. So thanks for you guys' time and listening to those sponsors. So now I'm going to kick it over to our moderator, Mr. Mitch Lund. You guys are probably familiar with the name and the face. He's been supportive of these webinars in 2021. He is an advisor to the DSUA board, and his primary function has been assisting with these webinars and the coordination. So he's done a lot in the background to help make these happen, including this webinar. So much appreciated for him volunteering his time. A little background on Mitch: he's a ChemE, and he's currently located and working out of Charlotte, North Carolina. He's got almost a decade working in air pollution control industry, developing APC solutions, specifically around DSI. Very solutions oriented kind of person, and will help you guys navigate through custom problems. So currently he's a technical consultant for, if you've got a dry scrubber problem, come to Mitch. He'll gladly kind of help you guys work with many different end users for those solutions. So, and previously he worked at Nol-Tec and was responsible for sales strategy and technology innovation in their environmental solutions division. So I'm going to kick it over to Mitch, and he's going to introduce our first round of speakers.
That's right. I appreciate the kind introduction, Jerry. Yeah, just everybody that's been watching these webinars has probably seen me, so I appreciate the introduction. I won't say anything more about myself, but yeah, if you guys need any help with dry scrubbing problems, that's what my focus is on these days, and it's what my passion is. So need help, I can be a resource. So all that being said, Today, I'm the hype man for our main event. We have both, as Jerry mentioned, Matt Wilson and James MannII from TVA, as well as Dr. Liu and Sean Dooley from RAS and Nol-Tec, respectively, on the docket today. We're going to start off with a presentation by TVA. Both Matt Wilson and James MannII are direct employees of TVA. Their presentation is entitled GPS Denied UAS Inspections for Scrubbers. And for the layman out there, UAS stands for Unmanned Aerial Systems. So we're focused on drone-based technologies in this first presentation. I'll give a little introduction. Matt Wilson. Matt started working at TVA in the year 2000 at the now demolished Widows Creek fossil plant in northern Alabama. Matt is focused on air pollution control and associated support systems for his whole career, and he's worked on everything: ESPs, bag houses, wet and dry FGD, ash handling, SCRs, DSI, anhydrous ammonia. Basically, if it's at a fossil plant, chances are Matt has worked with it, right, Matt? He's going to be co-presenting today with James MannII from TVA's Aviation Services Department. And a little background on James. James is an aviation services program manager that joined TVA in 2018. He has integrated this drone technology across TVA and was responsible for standing up its own department in 2019. So he's an innovator. We respect that at the DSUA. James has been involved with the aviation industry since 2012, and he specifically worked with UAS technology for the last 6 years. So let's give a welcome to James and Matt. And I believe, James, you're going to start our presentation off. So without further ado, I'll kick it over to you.
Thanks, Mitch. Pleasure to be here. Let's go ahead and get the presentation pulled up here. All right, Mitch, how's that looking?
Looks great, James.
Fantastic. So thank you for the kind words, the introduction. My name is James MannII, I'm program manager here with TVA. We're going to be discussing GPS denied UAS inspections inside scrubbers today. So the problem that we are going to be cognizant of throughout this presentation, are drone inspections worth it in a reduced budget environment? We're going to be walking through the different technology and equipment we use here at TVA. Matt is going to highlight the scrubber units themselves, and then we're going to discuss some challenges and considerations for operating aircraft in this type of environment, and ultimately we'll answer that top question there at the end of the presentation. So the GPS denied aircraft we use here at TVA, a couple of different products, and we can't formally endorse anybody, so we've got them all here on the screen. We use two products from a Swiss company called Flyability, the Elios 1, which is in the top left corner, Elios 2, and then the Interactive Aerial Legacy 1. Each aircraft has their own unique characteristics, and they're all collision tolerant. The Elios 1 uses a free-floating carbon fiber cage. Elios 2 has a fixed carbon fiber cage, and then the Legacy 1 uses a LiDAR anti-collision system. We do require here at TVA a FAA, Federal Aviation Administration, Part 107 license to operate any aircraft, indoor or out, and all indoor aircraft operations are performed by aviation services staff. That's their dedicated full-time job. And as we'll walk through the presentation, we'll talk about some of the challenges and why we've got the system set up that way. So our workhorse for indoor GPS denied inspections is the Elios 2 for a couple of reasons. Its stability in a GPS denied environment is very strong. So without the satellite system providing stability, we have barometric as well as gyroscopic stabilization. And then the Elios 2 also has stereo, visual, and IR camera stabilization. in tight environments. The video quality is good enough to do the inspections. It has a 12 megapixel main camera, records in 4K and 1080p video. We found over the last couple of years, we do most of our recording in 1080p due to file size constraints, and the quality that comes back both on the video recorded to the aircraft itself, as well as the backup recordings that go to the ground control station are really high quality. And our engineers and different stakeholders we work with inside TVA are very pleased. The aircraft does carry its own onboard lighting system. It's very effective for minimal lighting or completely dark asset inspection. And then we have about an 8-minute flight time across the board with all three products, the Elios 1, the Elios 2, and then the Legacy one has a little bit more. And that might not sound like a lot of flight time, but in the indoor environment, there aren't that many places to go. So we've found that that 8-minute range, we've really been able to adapt that to the type of inspections we need to do. Some auxiliary equipment that we carry with us on all jobs. The ground control station here in the upper right-hand corner consists of a controller and an Android-based tablet, pretty cut and dry. We also carry a large range extender. So we've got about 100 feet of extra antenna space, depending on what the asset we're inspecting looks like. Generally speaking, we fly from outside assets, so we're passing the aircraft back and forth through some sort of manway or hatch, and we usually bring the range extender out for any time we're doing research and development or asset discovery. If it's the first time we've ever flown in a particular asset, we bring the range extender just for that added bit of security. And then as well as anytime we have to go around 2 90-degree turns, so duct work, pipe chases, etc. We like that extra security because the first data stream that you lose when you have a weak signal is your video feed, which can be quite disconcerting in an unrecoverable type of environment. And then we touched on the 8-minute flight time. We carry around a lot of batteries as a result. Generally, I try to bring about 20 batteries and 10 chargers, depending on the job that we're going to perform. And then our trucks, our travel vehicles are also outfitted with inverters so that we can continually charge those batteries in case it's not feasible to access a power outlet, depending on where we're at. So we try to be self-contained as much as we can, and so far that's led to a really fair amount of success for us.
Hey,
At
James,
this point,
I got a quick question for you while I still have that image of the video from the 2 slides ago going through the scrubber. Is how challenging is it to navigate the drone? Because there's clearly, there's obviously a lot of nozzles and headers and stuff in there. It's kind of tight. How challenging is it to navigate through there? And if you wanted to like hold steady to focus on, say, a particular nozzle or an area in the piping or the vessel wall, how challenging is that?
That's a great question. So part of the discovery for any new asset that we're going to be working in is we'll have a sit-down meeting with the asset owner and go over the blueprints to make sure that we can even fit inside of there. Both flyability products are about 18 inches in diameter, and we look for about 2 feet of space, 6-inch clearance on each side. That way we can fit in through there. In terms of stability, that's where some skill comes in on the operator side. As I mentioned, each aircraft has a varying degree of stability controls. When we're in tight areas, such as the spray headers that we're looking at, the stereo camera and IR sensors do a great job of assisting the pilot in remaining stable. That way we can focus on a particular area of interest or managing the camera settings or lighting controls. But there are times where we're in a big open area, such as towards the bottom of this wet scrubber module, where the stability sensors aren't effective, and they can actually be debilitating. So the pilot having the skill and the experience to know when to activate and deactivate the stability sensors just is key in a successful inspection. So Matt, at this point, I'm going to
James, one more question.
Yeah.
This is Mitch. I'm sorry.
Sure.
Are there any temperature constraints on those drones?
We've got a slide towards the end, Mitch, that details environmental concerns. So we'll address that towards the end.
Sounds great.
But at this point, Matt, if you want to take us into the wet and dry scrubber piece, I'll drive the PowerPoint here for you.
Sure thing. Thanks. Matt Wilson, TVA Engineering. So the video was from a wet scrubber. We're going to go through a wet scrubber first, even though this is DSUA webinar. We've had the most experience now in 2 of our large wet scrubbers, and it's highly beneficial. So I'm one of the stakeholders. I work with a lot of peers at the plants and in field services engineering. And let's go through wet scrubber. So we first, the idea came up in spring of 2020. Aviation Services was asked, can you get in these scrubbers? And I think the answer was, well, let's try. So we tried. Inspection of main header piping was the primary objective. We've got reinforced fiberglass piping, so it's prone to erosion, as well as we've got a lot of nozzles that tend to plug. Camera stability and camera quality and aircraft stability was questioned since this is a large vessel. So once we got in there, though, we found that this could become a routine pre-outage task to help define scope for the upcoming outages, and we can do it all without putting in pick boards above 80 and 100 foot falls to below. Next slide, please. All right, so our case example is a 1300 megawatt unit at one of our plants. So it's got 3 absorber modules, high volume of flue gas flow, of course. It's a CE design, mid-90s. The absorber tank itself, 66 feet diameter. It's about 60 feet tall or so, 50 feet tall. And then we've got the spray tower diameter. And that's what the picture is on the right. It's looking up into the spray tower. It's about 60 feet diameter, and it's somewhere around 85 feet tall. You can see we got a large section of stainless steel wallpaper on the side, and then you get into this complex design looking up through multiple spray headers that are concurrent to gas flow. And every spray header is offset by several degrees to try to offset interaction between the spray cones, get good even distribution. Next slide, please. All right, so like I said, they are fiberglass reinforced plastic. We've got 164 nozzles per level, 5 levels worth per module. That's 820 nozzles. We've got 3 modules, so it's nearly 2,500 total nozzles. Now, the picture on the right is an obvious pluggage. Previous to drone inspection for pre-outage, what we got to do is open up the doors, and engineers, maintenance, they look across while the spray headers are spraying. That works really well for everything close to the doors. We only have doors on one side of the vessel, though, so it gets extremely difficult to discern what's plugged up on the opposite side of the module. Well, with this technology, you just fly the drones over there. Even the video footage, even though it did not have anything as dramatic as the picture on the right shown, it showed at least 3 plugged nozzles that were flush with the end of the nozzle. Well, all those take away from SO2 performance of this scrubber, as you're aware. And from the lower header to the floor of that tank, it's an 82-foot drop. So imagine getting out there across 82 feet. Even if we say pick boards, well, guess what? Somebody's got to put the pick boards out there, right? Make it safe for the inspectors. That's usually the carpenters. So we're talking about carpenter safety as well. All right, next slide, please. All right, so additional inspections, we can do spray header erosion. That's what I've got circled on the right here. So we can look up into the nozzles. We can also do a look down at the top of the spray headers, which receive the brunt of the spray slurry from the spray level above. So I've got circled an erosion area, and that's definitely scope that needs to be repaired on the next outage before that wears all the way through, breaks that nozzle and branch line off, and then we've got liquid slurry, either spraying straight up, or if it breaks completely off, spraying straight out instead of concurrent to gas flow. We can also look at all the hanger systems while we're in there easily. The rubber and stainless steel liners, the gas entry ring hood without an immense scaffolding cost. And I tell you, it is an immense scaffolding cost to look at the bottom and the top of where our flue gas entry comes in. Our flue gas entry comes into each module from a 48-foot wide by 29-foot tall duct. That is a large duct, and it is difficult to discern things on the top of that duct. So even going backwards in this scrubber application, this drone can easily get up to the top of that duct and see if we see any daylight, holes, major corrosion, water in leakage, etc. Next slide, please. Inspection durations. Now, this is from James, who has done the majority of the inspections. My peers have been with him a lot of the times. I've only visited, but again, I'm a stakeholder and benefit from scoping items, etc. So an experienced crew, every nozzle, about 2 hours per module. Complete inspection, all 3 modules in less than 1 day. So to get that done, that's a pretty quick fly through. We got 8-minute uptime, as James explained to us. We can, as we go along, we've got a nice good map that's been used for years and years at our plant. And they mark up what nozzles they see that are plugged as they go along. And they can reverse if we got a question, etc. As far as the erosion, that's where that post-flight video comes through, and the quality of the video also that James talked about. So what we do is one of our engineers sits down with this drone flight video and kind of frame by frame goes through it, reverses, fast forward, reverse, and from that they can highlight and fill in on their own leisure, on their own time, zoom in, etc. Where we have erosion damage seen. So all that goes into building our scope. So, you know, how much money do we need? That's always the question for a scrubber. Well, actually the question is, here's how much money you have, and then how much money do we need? And then argument ensues from there, or a technical discussion. So it really helps persuade folk, if you have data, here's how much erosion we have. It's not an assumption. This is what we got, and this is video footage. Now on the right, on this picture, we've got normally a slurry covered force oxidation header that's broken. Now inspections, they would have been able to see that something was amiss by uneven bubbles coming up through the slurry on the force oxidation. So we would have been able to see this with just a typical from the door inspection with a good light. However, what this does is, well, what's the scope? What's the repair scope? Is it just a break? Is it damaged brackets, etc.? So the drones allow us to get in close, see what we've got, get a video footage of it, and then base our scope on something that's real. Next slide, please.
Hey, Matt, before you go on, you mentioned you guys kind of have a mapping, I guess, that you follow. Like in general, if someone's looking to kind of utilize a drone, I guess how much have you guys from a strategic perspective kind of developed a strategy on how you utilize the drones and like what kind of patterns or how you do your inspections? It's not as simple as just flying a drone through there. I'm assuming your experience, you guys have developed I guess a strategy on how you're going to do this and execute it. And there's some thought to that. Can you explain to that in any way, your experiences with that and something someone looking to use drones should keep in mind?
Well, instead of past tense, I'm going to say that we are developing, right? Because this is a still developing technology for us. And we're only talking about GPS denied inspections for these drones today, but James is involved in a lot of other inspection tasks. So in this case, for our pollution control equipment, that's what I work on. We already have lots of inspection sheets, and we always tried to populate them as best we could using the only means we had, visual eyeballs. Some areas you had to physically go into the duct, or into the equipment. You got to climb, you got a scaffold for access, etc. So what this allows us to do is inspect things essentially from the doorway. Usually we don't even have to break the plane, except maybe to reach in and get the drone, recover the drone, etc. As far as getting inspections set up, talk about a huge time saver. You still have to have the unit cleared, of course, or the module cleared. But you really are able to get in there, complete your inspections quick. Confined space, no one is entering the vessels. You don't have to do a confined space permit. It's just the drone, and the drone doesn't take any breath, right? So it's really improved our access, but really it's just utilizing our existing inspection sheets. However, I think there's always room. A lot of the inspection sheets were blank, right? Just maps, top-down views. I think it leads into the opportunity, like probably a lot of us have. We have pre-populated items. Item 1, broken forced aux header. Well, instead of trying to write out broken forced aux header, put a number 1 on the map, for all your expected findings. So there's always room for improvement on that. We're trying to do that.
Thank you.
All right, next up, we have gotten a drone into one of our dry scrubbers. So we attempted this in fall of 2020 with some success. Inspections completed as needed due to favorable reliability. And what we were looking at is savings, and this is real savings because unfortunately, just this spring, we thought we saw something in one of these same 90-foot tall reactor ducts that we're going to be looking at still shots from. And we built scaffold up to it to access it, look at it, and repair it. And it turned out there was nothing to repair. It was just a construction shadow line. So we expended about 88 carpenter hours on that versus, an easy 10 minutes of drone or 8-minute flight time would have been able to clarify that without any issue. And we could have saved all those carpenter hours. So we're still learning where we can apply this and trying to remember when to apply it across our whole fleet, right? Because we're a lot more than one plant. So the case inspection comes from 275 megawatt unit. We got 4 absorber modules or dry scrubber modules. This is a 2010 design Alstom, now GE, of course, novel integrated deacidification unit. So that's a NID. And the biggest place that we could apply this technology is the 90-foot tall reactor duct, which is all aligned with a AR plate, abrasion resistant plate. And the view on the right is kind of at the bottom. You see in the bottom left hand of this screen capture, we got 22 feet up from where we put the drone in. So this does keep up with where you're at. On the bottom right, that was the bottom left, on the bottom right of the still shot, we've got orientation and direction. How far away are we from walls? What direction are we turning? James especially can utilize this to help fly and reorient himself, but it's also beneficial if you're going up and 90 feet, you might lose track of exactly where you're at. Well, between these two key points, especially on video recall, you can get a really good idea of where you're at, where you see an issue. All right, so that's looking up our 90-foot duct. Next slide, please. All right, and so this dry scrubber example, it is a full burden. So we've got byproduct and fly ash. We've got a recycle system on this design, which means we have a huge amount of particles in here. So the AR plate is to resist erosion. You can see some polished area on the top of this screen. So where we're at is now we're 73.8 feet up from our original starting point. We're near the top of our J duct is what this calls, or reactor vessel. You can see that it's starting to turn over from vertical to 90 degrees over to go horizontal. In the view, you got that polished area on your right, kind of the sloped roof section. We have to keep an eye on that, right? It has that eroded through, has it popped the plug welds? Do we have water entry, etc.? Kind of in the middle, you've got an access door in the roof. You also have your activated carbon injection lance. Is that plugged? Is it there? Is it eroded and gone? And then we've got our gas distribution half pipes on the left-hand side view. Next slide, please. And then here's fully oriented facing those gas distribution pipes. And, questions here, are we completely plugged? Are we eroded? Do we have things broken down, etc.? Since it is a dry scrubber, as we're all aware, if your moisture gets off too far, you are prone to pluggage. We're all fully aware of that, and pluggage creates havoc in gas distribution, and it snowballs on itself, right? It causes even more problems, performance and particle capture ways. So other inspection potential where the recycle hydrated lime enters the reactor duct, we got to look for pluggage there and erosion. We already talked about the AR plate, gas distribution, and of course the carbon injection lance. So the major obvious advantages. These are areas of this reactor duct that it is difficult to put eyes on. This turn and looking at the inlet of these gas distribution plates, you can't see it unless you build scaffold up. Right now we're 70 feet up from our starting point. That's a heck of a lot of scaffold. It's especially a heck of a lot of scaffold to get up and then realize, all right, nothing's there, tear all that scaffold down. We don't want that. We also want to proactively look at these items, and this the drones enable us to do that before we are reacting to maldistribution or performance issues. We want to catch it early. If you catch anything early, then it costs less money to fix it, right? All right, next slide, please. And I'll turn it back over to Jim.
Yeah, thanks, Matt. So there was a question about this earlier. The challenges and considerations for the environmental conditions are at the front of our mind as operators constantly. We touched on earlier reviewing the blueprints and schematics to make sure we have enough space to operate around. We also try to look for areas that could reach out and hook on to the cage, because that also presents a problem. Dust and debris, especially in the dry scrubber, is a constant concern depending on when we're able to do the inspection during an outage. Visibility could be very limited, which makes the inspection difficult. If the operator can't see where they're really looking, then the video that the engineers review later is going to be adversely affected by that. On our large scrubber modules, drafts were a concern that we had not considered until we showed up the first time to do an inspection. There's a very strong draft coming in through this door, and our aircraft are not able to fly back out through this door because of the draft. So what we've learned to do is we come to the side, either the left or right side, and then the visual observer will reach in and grab that drone. So all of our drone teams work in two-person crews. They both have the same level of experience, and given how this is a new technology and we're really pushing the equipment, the hardware to its max, it's really helpful to have an extra pilot there with you talking through these considerations. If problems do arise, you're able to troubleshoot as a team, and it's a very effective way to manage this type of work here at TVA. Some other considerations: humidity. The drones run off battery power. They're electrical equipment. If we have too much humidity, fog can form in these large assets, and they don't mix well with water. And then the last big one that we haven't touched on is temperature. This equipment is good up to about 100 degrees. Above 100 degrees, we start to get really nervous because different electrical components can shut down and cause loss of power to the aircraft. So between 100 and 120 degrees, we start to implement stay times. We limit our flight times depending on what the known temperature or expected temperature is, and we monitor performance after each flight to see if any components are overheating. It hasn't been as much of a problem inside of the gas or the coal world. Gas and nuclear are a little bit more of where we see our temperature problems. And then signal strength we touched on earlier. Like I said, to reiterate, we bring that range extender out with us generally the first time we're doing a discovery flight, and then depending on what signal strength looks throughout that flight, we may jump to just the controller itself.
Just before you guys start the slide, just want to give you a heads up. We got a 10-minute warning. So just 10-minute warning, okay?
Sure. So our overall question that we asked beforehand, are drone inspections worth it in a reduced budget environment? I think for us, it's a resounding yes. From the inspection side, not being an engineer, I see tremendous value from a safety perspective. We're limiting inspection hours from building scaffolding in confined spaces at hazardous heights, and it allows the different stakeholders to formulate a real empirical plan based off of repeatably captured visual data. We start to build a record over time, and that's just a tremendously valuable trait to have when it comes to managing, maintaining these assets. Matt, do you have anything to add?
I wanted to add, being with you a couple weeks ago, the high dust environment, which we tried to inspect a precipitator inlet duct for normally some vertical and slope duct that's typically inaccessible to us. We didn't have complete success though, due to so dusty. So I guess the analogy that I was witnessing, even though I was not flying that drone like you were, James, is you alluded to it. When it gets too dusty, you're around a corner, you can't physically see your drone, and you lose video footage, and you're just dead in the air. The analogy that I can think of is kind of like when you're driving along the interstate at night and you fall asleep. And then all of a sudden you wake up and you wonder, now, just where in the heck am I? Am I about to wreck? This drone, it's not a low-cost piece of equipment. It takes some investment, doesn't it? Could you give us an idea, at least for some of these products, how much it costs?
Absolutely. So generally speaking, for any indoor GPS denied aircraft worth its salt, you're going to be looking in the $20,000 to $50,000 range. Our equipment ranges from about $35,000 to $45,000, and that includes all of the extra batteries, any spare parts, technical support, etc. And then if we were to bring in contractors to do this, we're looking at anywhere from $5,000 to $10,000 a day. Now, TVA is a large enough entity with enough assets across the enterprise, not just in the fossil silo, that the upfront capital cost of having our own in-house equipment is highly beneficial, and we've paid for our equipment several times over in the past 2.5 years that we've been operating with it. But those are some of the considerations that you need to make before deciding to purchase, contract, or whatever you decide.
So thank you, James. And we have another question on the drone. I'm going to call it the evolution itself. So we have a question from audience member Kevin Redinger asking if we can integrate a temperature sensor on the drone. And I wanted to package that kind of just from you guys' experiences and any cons you've seen with this technology. Are there ideas that you have in-house that can improve upon this even further?
Yeah, so a great question. We carry temperature sensors, something we bought off Amazon and have Velcroed to the top of the equipment that we can check on our ground control station tablet. We can't necessarily do it real time because we've got the application to run the aircraft up. But once we complete that first flight, again, if we're unsure of the temperature, we're going to reduce those flight times. But after that first flight, we're able to check the temperature sensor, and then the aircraft itself will give us an evaluation of its health, if you will, after each flight. So we're able to track it in near real time, and we've really done a good job coordinating with the different plant operators, looking at the different sensors that they have throughout the plant itself to give us a better idea of what we're getting into from a temperature perspective.
Excellent. And I had one more question for Matt as the stakeholder too. So Matt, I understand that you've obviously seen tremendous benefit applying this technology and the inspections. Is this approach now basically your standard moving forward as a stakeholder, or are there definitely other applications where more of a traditional approach might be more suitable from your perspective?
I'm going to say this does not replace the physical inspection, like in a major outage. It's another tool in the toolbox, and it complements. The wet scrubber, the spray header visual inspection, we're still going to do that. You can get really beneficial information from that. Again, this complements that inspection. What's going on the other side and the hidden areas you just can't see. So using the two together really gets us to where we need to be. And then I alluded to it, you know, the carpenter safety aspects, the personnel that get on all that scaffolding, every outage, just like probably everybody on this webinar, I'm constantly amazed at all of our carpenters that put up the scaffolding. They really put themselves in harm's way, right, to provide access for inspectors. This is an opportunity and a tool that we can help their safety by keeping them at, it's man-hour saving, it's cost saving, but it also keeps them out of harm's way just to get a solid visual inspection, get some pre-outage scope, and not to mention the confined space aspect. If you can get by getting a good inspection visual without sending somebody in a confined space, that is a terrific investment.
Excellent, excellent. Well, I know that we have about 4 minutes left. Jerry, I believe you maybe had one more question, and I know that you guys have one more case study, but maybe Jerry, we should get to your question first and then see where we're at.
Well, I think it's kind of a general set of questions, but you know, for say the end users that may watch this, you know, how and find this interesting, I guess, how do you get started in terms of, you know, how do you start going down the path of this solution in terms of finding the right drone, getting in touch with the right people, and much like James, you said that there's kind of a little bit of a, I guess, a science and feel to actually flying the drone. So, you know, if someone wants to utilize this and do they develop this experience internally? Are there companies that will farm this out and do this for them? But how would a new end user looking at this kind of go about, you know, evaluating and implementing the use of drones as another tool to add to their belt?
Sure. Another great question. So we did a tremendous amount of industry benchmarking before standing up a drone program. So we went and talked with our sister utilities here in the Southeast and across the country. We benchmarked with the robotics and unmanned aircraft industry quite significantly for about 12 months as well. And we basically called anyone who would pick up the phone and asked them the same question. How did you start your program? What has worked well for you? What hasn't worked well for you? What lessons can you share? And people were tremendously forthright about what they had learned. And we were fortunate enough to have leadership that was willing to innovate in this direction. And it worked out really well for us. And after all the benchmarking, we came up with a plan to have folks either trained or bring in people both internally to TVA or externally who had the experience with unmanned aircraft. They had the stick skills, if you will. And I think you'll find that there are a lot of people who are into RC aircraft who have, you know, maybe a private pilot's license or who have been using you know, aircraft at home, using drones at home for the past several years. So it's pretty easy to find the right folks, if you will. But we were fortunate enough that our leadership kind of turned us loose and let us be aggressive and deliberate with our integration, and it's worked out really well. But there's, as the technology propagates, more and more folks have lessons learned and are willing to share their experiences, and that's how we were able to stand up a program, was on their knowledge that they were willing to share with us.
That's great. So it sounds like whether you want to, like you guys went the path of doing it fully internally, but if someone wants to just completely hire someone externally to do it, they have some optionality to decide which path makes sense for them by the sound of it.
Absolutely.
Thank you.
Well, excellent. And I know we're actually going to extend this a couple minutes because Matt and James, I really want you don't have to necessarily do a full-on presentation, but these slides are going to be part of the DSUA archive. But Matt, maybe I'd like you to also go through the next last couple slides about applying this to a silo too. I think a lot of our attendees will find this beneficial. So go walk through that real quick if you don't mind.
All right, bonus round. I love it. All right, so byproduct, it's slightly moist, as we're all aware. But if it gets really moist, then we have a major problem. So this is a case example. It's actually an abandoned fly ash silo on one of our sites. And James and group was able to do an external structural inspection, and then we're able to pop into the inside. So it's 35 feet diameter, 65 feet tall, 1970s design. Definitely have to, side note, our structural department for all stacks, all silos, all coal silos, coal bunkers, it is getting stronger and stronger, more and more strict. The drone really complements structural inspections. And talk about scaffolding. I mean, you can't go up this stuff. You can't build scaffolding high enough to inspect our 1,000-foot stacks, right? Next slide, please. So we put the drone down in the top of a empty dry fly ash silo. So inspection potential for fly ash or byproduct silo. Well, number one, I was thinking we got water entry, fly ash level drawdown, and instrument inspections. So in this case, we're looking down. So yeah, this thing's empty. You can fly the drone all the way down to the bottom. Next slide, please. And it's interesting, we came in from the top. So you see down in the lower left-hand corner of our picture, we've got negative 14.4 feet. So it's at the 0 level for the start time at the roof, right? We went in through that roof hatch. So we got some major scaffolding savings. You can complete your roof inspections without any drawdown. You don't even have, you know, how do you do your internal roof inspections now? Well, you got to get inside. You got to get a high power flashlight. You got to look 65, 80 feet up in the air and try to look for a wet water entry zone. And that means somebody's got to go in. So isn't it always a precarious situation when somebody's got to open that lower door that's down at the bottom of potentially a 65-foot head? And TVA, we have struggled through plugged fly ash silos, not byproduct silos yet. That water got in here in major proportions, and we had some extreme buildup. So when is it safe to open the lower access door? This 8-minute flight time quickly complements. You stick the drone in, you can see if it's safe to open that bottom hatch. You don't even need the level out. You can drop it in, look up, get close to the roof. Even though this was a dirty inspection, and later on in this video, it kicked up a good amount of dust, aviation services was still able to get good flight time, look for water entry, etc., especially at the penetration points. You see in the lower right-hand corner of the captured screen, you see the bottom of bags, you know, from our little bag house that's on top of the silo. So you can see the condition of the screen that's on there that we actually have to walk on to change those bags out. Always, again, precarious situation. All right, I think that's it, Mitch.
Well, that's great stuff. I like to keep stuff on time, but when you're talking about cool stuff, we're going to ask you to stay longer. So I really appreciate both you guys sharing this story. I think it can apply to a lot of our group members and fans, attendees, if you will. So really, thank you very much for putting this together, Matt and James. And I think now is about the time when we stop, as they say, for a commercial break, Jerry. So maybe I'll transition it over to you, okay?
I appreciate that, Mitch. Appreciate that. So let me, I will share my screen. Hopefully you guys can all see it. And again, I'll go quick here, but again, I would definitely like to acknowledge some more of our sponsors. And, you know, right here, GE is a name that, you know, we've all heard of. And again, you just heard, you know, Matt and James talk about one of the NID systems from GE. So again, they're one of our sponsors. Obviously, a large power portfolio, whether it's steam power technology for fossil nuclear applications, whether it's a boiler, generator, steam turbine, AQCS system. You know, they provide a multitude of performance for the life of the plant, and they're all over, not just on AQCS, and they're a global company. So, you know, they've got about 30% of the global steam turbine capacity, as well as about 50% of the steam turbine capacity for a nuclear power plant. So, and about 30% of the world's boilers are GE boilers. And they got about 1,500 steam turbine module retrofits out there. So again, they're solutions oriented. They're going to help their customers with best in class, you know, equipment upgrades and retrofits to their core operations and maintenance. So they've got over about 90 different OEM brands, and over 6,000 field service employees that are, again, delivering solutions to help ensure, productive future for the coal and nuclear power plants that are out there and running. Travis Reynolds from GE, he's a vice president of DSUA. And again, he's been really instrumental to supporting DSUA as we've kind of evolved with these webinars in the last 2 years. So a big shout out and thank you to him specifically. And again, if you want to learn more about some of their technologies, Matt gave a presentation back in 2020 of September talking about, GE's NID technology. So that would be another good one to go check that out. Lhoist North America, they're a subsidiary of the Lhoist Group. Also, they're a global limestone, quicklime, hydrated lime, and silicate minerals company. Primarily in terms of dry scrubber users, a big topic of discussion has been their enhanced hydrated lime sorbents, or Sorbical SP and SPS, that are engineered in order to optimize dry scrubbing solutions for acid gas control. So whether it's a DSI or a CDS system, it's another tool for to help optimize solutions at whether it's a coal-fired power plant or a multitude of industrial facilities. So as well as their technical team is able to help you guys provide custom solutions in terms of developing a DSI solution or optimizing it. You can learn more about that back if you want to catch up. Listen to Ian Teratovsky of Lhoist gave a webinar back in November 2020 about the use of DSI in conjunction with other integrated dry scrubbing solutions or just as a standalone solution. So there's another webinar out there. Welcome, go check it out if you haven't seen it, as well as Lhoist recently put together a platinum podcast video too. So, that's something you're available to check out. So thank you, Lhoist, for sponsorship. And this is someone you're going to hear more of, Reaction Analytic Solutions. They're going to be given our second presentation coming up, and you'll learn more about their specialized engineering solutions for these CFD models. And Dr. Guisu, he's been doing this for over 2 decades, and whether it's fuel combustion or emission control industry, and he's been developing over 100 CFD models based solutions to address whether it's the front end or the back end. So again, whether it's combustion related or flue gas treatment, Reaction Analytical Solutions can support with the CFD model based solution to optimize the chemistry. So whether you're going to hear about DSI or ACI, activated carbon injection, are also great applications for utilizing CFD to try to optimize a solution. So you're going to hear from him in the next presentation. And National Filter Media, they take pride in being one of the oldest as well as one of the largest provider of air pollution control and liquid filtration products. Even though that they've been around since 1906 and the industry's changed a lot, they still adhere to the same business principles since they started. And ultimately, they believe in developing partnerships with their end users and selling solutions as opposed to just selling equipment, and on a daily basis, trying to earn their customers' trust. So again, the filtration technology has changed a lot since 1906, but these principles are important to these guys, and they've sustained them and supported the dry scrubbing industry since then. Primex, they provide comprehensive help for dry scrubbing applications. So SDA, CDS, DSI, they're going to help you guys try to optimize the performance, operation, address issues. They've got over 2 decades of customer success that they've demonstrated through a unique combination of their knowledge, their expertise, as well as patience. And you can see a list of some of their clientele here. The best thing you can do, you want to learn about Primex, Stuart Nicholson has given a couple presentations at these webinars. In 2020, he gave a great one talking about the use of approach temperature control for a CDS at Dry Fork Station and how they worked with them to optimize that solution. Very interesting. And then earlier this year, he gave another one in terms of optimizing SDA performance through detection of the slurry atomization anomalies. And again, something super interesting. So they're out there. Please go check them out, and you'll learn more about what Primex and Stuart, those folks, do. And real quick, last, you've seen a lot of these names, but again, big thank you to everybody that's on this list. And whether we called you out with a slide or not, these guys have all in the industry supporting dry scrubbers. And if you want to get in touch with any one of these guys or learn more about them, go to the dry scrubber link homepage. You can scroll down. You can get through all these guys' home sites, their web pages. But if you need to get in touch with any one of them, just don't hesitate to reach out to us. Give us a shout, and we'll gladly connect you guys. So All right, now having said that, again, thank you to our sponsors, and I'm going to turn back over to Mitch, and we're going to get on to our second presentation.
Yeah, so as Jerry mentioned, our next presentation is going to be presented by Dr. Guisu Liu of Reaction Analytics Solutions and Sean Dooley of Nol-Tec Systems. The title of the presentation is called Sorbent Injection Performance Improvement Using Chemistry-Based CFD Simulations, which is a very powerful tool. I used it myself. I'm really excited for this presentation. Before we get into it, I'm going to give a quick background on Dr. Liu and Sean. So starting with Guisu, for those of you that have been part of the webinars, this is probably the third or fourth time I've done an introduction for Guisu. So I'm close to committing this introduction to memory, but not quite there yet, Guisu. Guisu has a PhD in chemical engineering from Australia. He moved to the United States in 2001. And since he's moved here, he's been working in power and emission control industries ever since. Guisu previously worked for Mobotech, Nalco Mobotech, and AECOM before he founded his own company in 2017. That company, again, is called Reaction Analytical Solutions. They focus on performing CFD services with focus on chemistry and chemical mixing to optimize chemical utilization in flue gas streams. Very relevant to what our focus as an organization is today. Guisu has published 6 patents. He's written over 130 technical papers. In his free time, when he has it, he raises his family and gets a run in occasionally, some exercise, right? So next, also presenting with him is Sean Dooley of Nol-Tec Systems. Sean has a degree in civil and environmental engineering from Illinois. So he's a Big Ten guy, which has a soft spot in my heart. Sean has worked in stack testing and SEM service industries for heavy industrial clients since 2011. He joined Nol-Tec Systems in 2017. His focus is on providing capital equipment solutions for end users needing DSI help. Unfortunately, Sean is a Packer fan, but he resides in Chicagoland to get over the depression that comes with being a Packer fan. I'm a Vikings fan, so I'm biased. But anyway, I'll transition over to Dr. Liu and Sean, and you guys take it away from there.
Thank you, Mitch, for the introduction. So as the title says that, for some of you that have experienced using the CFD to help you in your design process, this is something about expanded capability of the CFD by incorporating the detailed chemistry. So we're going to focus on what is that means inside of this chemistry and how we can benefit by this expanded tool. So I'm going to start with this overview slide, and I'm sure many of you are familiar with the solvent injection and how it's being applied in utility boilers or the industrial facilities. So you talking about the different kind of solvent, the limestone, the hydride lime, the sodium-based solvent, or even activated carbon. So, and you are injecting this solvent in a different location of the furnace, or even, the duct work, before and after air heater. So your goal is trying to remove the, SO2, SO3, HCl, or even mercury by, injecting the activated carbon. Now, as we know that, the performance of the solvent injection is really affected by many of the operating conditions, including the temperature, the time, the particle size distribution, the properties of the particles, like the porosity, surface area. But most importantly is, what is the coverage dispersion with the flue gas, and what is the injection rate that we need to inject to achieve a certain reduction goal, and also, different type of, the particle collection device. So all these different operating factors is going to affect your performance, but ultimately the chemistry and the reaction is the fundamental to, to chemically determine, how those factors, will affect your performance. Now, let's get into a little bit basic about the solvent reaction process. So when we inject, solvent and into a hot flue gas, so the solvent, can go through some of the thermal decomposition. For example, if you inject a limestone, you're gonna have some calcination happening, same as a hydrate lime. And for sodium-based solvent, once you inject it into a hot flue gas, it also goes through some of the thermal decomposition. Now, what's the end of the thermal decomposition is you're gonna have a fresh, the calcium oxide or sodium carbonate to further for the reaction. But also you're gonna have some the particle physical process that is changed. For example, the porosity and the surface area. So all those will be changed. Now, after the decomposition, it's followed by the called a sintering characteristic. So essentially that some of the particle will become a type of like a melting phase. Well, you actually gonna reduce the porosity and the surface area if you inject at too high temperatures. So those things also matter when we consider the the injection temperature specifically, how that's gonna affect the performance. Now, the most important is probably be the reaction chemistry and the kinetics. And for each of these calcinated the solvent and how it's going to react with a different species, and the kinetics and the chemistry really kick in to dominate the process between the particles and the species. And in all this kinetics, the boundary conditions, the diffusion and the pore diffusion will come into play and become a significant role in all these reaction mechanisms. So all this reaction we're talking about here, it's all governed by the rate equations, which we can ultimately develop mathematical models to describe that. So to develop the submodels to for these reactions and incorporate that into a CFD code, we actually started with a single particle, just like this diagram illustrated here. So when we have a single particle, the gas species is gonna diffuse and through the boundary layer of the particles, and it may diffuse continuously through a pore diffusion and get into the inside of a particle and for a chemical reaction. So if you talk about like a single particle reaction mechanisms, you probably already heard about the chemical reaction and the diffusion, and both actually become quite important. For us to develop a model, and we have to combine both chemical reactions and incorporate the diffusion for the boundary layer and also inside the particle, and later the model to decide what's the ultimate reaction regime at a certain operating conditions. So we develop a model, we incorporate all this process here in our model, and we have an input of using the solvent property, like surface area porosity, the size distribution, and also most importantly is we incorporating the flue gas operating conditions like flow rate, temperature, species, concentration. All those things will ultimately affect the performance because this is all chemical reaction related. So we incorporate all these mechanisms into a code, and we incorporate those code with a CFD so that we become a more powered tool for making predictions. So over the years of time, and we have expanded our capabilities to almost include all kinds of the solvent related the reaction mechanisms. So hydrolyne reacting with SO2, HCl, and SO3, same as sodium based solvent to react with this solvent. We also recently expanded our capability trying to include the activated carbon reacting with mercury species. So all these mechanisms have been developed. And as you can probably already feel that, with that certain tool, and we can, help the utility operators, the engineering designers and the equipment suppliers to help them to optimize, whatever they can do to, optimize the system and to get a better efficiency. So this table is probably summarize the overall capability, especially in, compared to the traditional, the CFD model. So with the traditional CFD model, of course, you can do a lot of prediction as well. So particularly looking at the particle trajectory, the particle dispersion, you can calculate the RMS at a certain cross sections. And in a certain way, you can use that model to help you to optimize your injection strategy, at different locations, or looking at a different mixing device, trying to help optimize the system. But with the chemistry-based CFD model, you can do a lot more things, because with the chemical reaction, it can give you the fundamental reactions and how to relate to your the species and all those pollutants that you care about. And with that capability, of course, you can use that to evaluate a number of different operating parameters, and also even the solvent properties, because the solvent size, porosity, all those properties will be an input as our model. So in the next case studies, we're going to talk in a little detail about how each of these model will help us to optimize our solutions in a detailed way. So, with that tool, in our last maybe 5 to 8 years, we actually help a number of engineering companies and utility owners to help them, especially looking at the different ways to enhance the mixing, the particle dispersion. And this is just a number of ways to consider to enhance your mixing. And we have to look at many types of mixing devices. So just some experience to share with you about the applications of our models. Now we're going to start with the first case study. This is a case study that we did a few years ago. Well, it involves the GRE Stanton unit station in North Dakota. And it's a 200 megawatt front wall fired burning a PRB coal. So the goal for this project is to using a dry solvent injection technology to reduce the SO2 from the 0.55 pounds million BTU. And the goal is trying to reduce 70% of SO2 reduction. So this trial project was sponsored by APRI, and so we tried 2 different solvents. One is the hydrolyne, and the second solvent is the Mitch-Lund. And so the injection, we started with the traditional lens injection. But in this project, we also looked at the enhanced the mixing device, which we're going to talk a little bit more. So this is a diagram of the flue gas duct. So you're going to start this is the DSI injection locations. it's upstream of the air heater, and you have a certain flue gas duct before the flue gas reach to the ESP. Now, as a typical the CFD model, so we'll look at the particle concentration distribution, started from injecting from a DSI lenses. So you can see where the particle go and also understand how the particle mix, with the flue gas in your duct and it goes through the ESP. And in addition to the particle flow and the dispersion information, with the chemistry model, we can simultaneously predict what is the SO2 reduction and what is the HCl reduction. So in combine, all this information together, you can have a full understanding on how this solvent will perform as far as the dispersion, as far as how to react with different the species. Now, just some data to show you. So this is the trial data collected by injecting the hydrogen lime. So you have some SO2 reduction versus a calcium by sulfur ratio, and that's what you typically collect the data when you do the trial. And we also have a CFD prediction for the same configuration and the same solvent under the same conditions as the trial did. So at a little bit higher calcium by sulfur ratio, we got roughly about 50–60% of SO2 removal rate, and the CFD really captures the reduction level, quantitatively very well. Now we do have a little bit over prediction of the CFD, over the trial data, but in general, the CFD gives a pretty good agreement with the data that we collected for this run. Now this is the second the data by injecting Troner particles. So obviously the Troner at a high injection rate, a higher NSR, you have a more SO2 removal level, and the CFD actually predict quite well compared to the trial data that we collected for the SO2. At the same time, we also have a data point for the HCl reduction level, and this is how a CFD we predicted. So there's some difference here as far as the data versus the CFD prediction. Now, the second case study is about the injecting the hydrogen lime to remove SO3. And I know that SO3 removal and in terms of the dry solvent injection in the United States, a lot of activity about dry solvent injection is to remove SO3. So with this tool here, it's actually can help to optimize their injection quite well. So this case study is a 450 megawatt coal-fired plant equipped with SCR. So the geometry we are considering is at the bottom of the economizer, and you will go through the air heater, which is around here. So the goal is trying to design and optimize the lens injection system for SO3 removal. So first of all, we got some the velocity distribution as our flow model, and this is a pressure distribution along this flue gas duct. Now the next thing is we all did 3 cases for the lens injection, which is right upstream of an air heater. Now in these 3 cases here, there's 3 different depths of the lens injection. As you can imagine that, different depths, of course, it will have some impact on the particle dispersion downstream. So this model exactly show how the lens design and how the SO3 removal, downstream is going to look like. So, the first, single depth is, so you end up having a SO3 removal rate about 61%. Now, if we consider two different depths of the design, we actually improve the reduction level from a 61 to a 75. Now, if you continue to, let's say, consider 3 different depths, you only improve by, 2%. So, this definitely can tell you that maybe the 2 depths is good enough for our system. Now, let's look at another factor, which is a number of lenses here. So we look at 2 cases here, the 6 lenses, the 2 depths, and the 8 lenses, the 2 depths. So the reduction level has been increased from 75% to 77%. So, it really depends on your reduction goal you're trying to achieve. And also by increasing the number of the lenses, of course, it's going to increase your cost. So it's really the balance between the performance you want to achieve and the cost you want to spend. But the prediction of the CFD give you a very good indication on what the system can give you and give you a choice for making decisions. Now I'm going to give the case study number 3. So this is a project that we did for a waste to energy plant in the UK, burning a meat and bone meal type of a fuel. So this boiler is a 72 megawatt thermal, so it's really a small boiler, and a DSI has already been installed to inject the sodium bicarbonate to remove both SO2 and HCl. So the customer owners has reached out to us trying to see if there is a way to help them to reduce the solvent usage. And using a CFD, we look at 2 of the solutions, for this case. Number 1 is they had a 1 lens, but we're trying to look at if we increase the lenses from single lens to 2 lenses. Secondly is we trying to think there might be a way to relocate our injection lens to gain some of the resonance time, and that might be some benefit. So we looked at these 2 solutions, and this is a CFD results. I'm not sure if you can clearly look at that. So this is a flue gas duct inlet coming from the bottom of the economizer. So we build a duct and we all the way to the back of the inlet. So this is the location for the existing single lens. So during our study, we looked at the 2 solutions. One is to increase the number to 2 lenses. Secondly is, we are moving the injection locations to upstream. And so the bottom 2 figure is the SO2 and HCl concentration predictions before the retrofit and after retrofit. So it really helped us to quantify by, to executing those 2 solutions and what's the benefit of it. So at the end of a simulation, we also can create this kind of a performance curve where the reduction level versus the NSR. So it's really a benefit that we can, get this kind of curve for us to, perform, the cost of the saving analysis. For this case here, so by incorporating those two solutions, we are predicting that about 23% of the solvent savings can achieve. Now, the project has already been executed, and after executing those two solutions, we did achieve the solvent savings by 12 to 24%, and so it really shows the benefit of using the CFD to confirm the solutions that in your mind and give analysis, so you can have some the engineering solutions that you can make decisions on. Now we're going to spend a little bit more time on discussing this most recent case number 4 here. So it's
Guisu, real quick, sorry to interrupt.
330 megawatt, and it's got a SCR to remove a NOx and ESP to remove a particulate. So the DSI, the solvent injection with sodium bicarbonate to remove SO2, that's our goal here. So if you look at the furnace flue gas duct diagram here, so we built a model started from economize outlet, and the duct go horizontally and then go vertically upwards and then go through the SCR. So at the bottom of SCR, the duct go horizontal and have a couple of turns before it gets to the ESP. So this is the entire system that we built. Now, in our CFD, we looked at 3 injection locations for the sodium bicarbonate injection. One is consider the pre-ESP. So this is somewhere around here. And the second location is pre-SCR injection locations, which is post-SCR. So that's right at the bottom of the SCR duct. And the third location is the pre-SCR. So you can imagine that with these 3 locations, of course, it's having different residence time, and the CFD prediction can give us some quantitative indication on which location is going to be the best for the utility to decide and for their trials.
Hey, Guisu, real
now,
quick.
I'm going to give some results of the CFD simulations. So this is the summary for the pre-ESP injections. So this is the particle trajectory. So you can see the particle injected from the lens, and you end up having about 2.5 seconds of residence time before the particle gets into the ESP. Now this is a particle concentration distribution. So between these together, you can have a sense of your injection system, whether that's give you the best particle dispersion or not. This is the ultimate SO2 concentration prediction. So, and that's where the SO2 has been reduced, and ultimately at the calcium at the NSR of 0.71, we predict about 34% of SO2 removal for these injection locations. Now let's move to the post-SCR injection. So this is at the bottom of the SCR. So the particle has a longer resonance time. It's about 4.5 seconds. And the particle distribution, you can see that after the injection, it gives a very good particle distribution in the duct before the ESP. And the SO2 concentration also gives you a better understanding how the resonance time and the dispersion can help you reach what is the SO2 reduction level you can get, which is predicted about 55%. Compared to pre-ESP, the injection locations, This is about 20% of SO2 reduction level improvement. So it's quite a significant. The next location is pre-SCR. Of course, it's probably give you the longest the particle resonance time as possible, because it's almost like 15 seconds as it's going through the SCR. And the particle dispersion is very good, and even with a lens injection. Now this is a SO2 concentration as a consequence of the injection of the solvent. Now overall, we are getting about 64% of the SO2 removal rate. You know, compared to the post SCR, so your resonance time is more than double or even probably triple, but the SO2 reduction is we only gain roughly about 10%. So it's not a significant jump as your temperature, as your resonance time getting longer, but certainly that help us, the model will help us to understand, what a magnitude of the improvement that you can get by, the different locations and how time is impact. Now I'm gonna hand over to my co-presenter, Sean Dooley from Nol-Tec, to talk more about the trial and the trial results. Sean?
All right.
Hey, Sean, before you start speaking, just want to give you a heads up that we're looking at 4 minutes, 4 minutes left in the presentation, if that's cool.
Yep, that's good. Okay, so just to take it from Guisu's CFD model to the physical trial, that's what most of my information is going to cover. We had to figure out a test protocol, and we had to figure out how to get resources on site. So we brought in a mobile silo, all of our mobile injection equipment for this. And we also had to work with our sodium bicarb supplier to get pre-milled product, because using mills on site wasn't really an option or economically feasible. We also had to tune up and make sure that all the monitoring systems were in place to actually get usable data for this. And I thought this was a really important feature for the success of this trial, even though it was usually kind of overlooked when we do these things. We were using coal samples to measure the inlet sulfur content. And then we were using the stack SEMs, and they had just had it calibrated with method 6C to monitor SO2 during the trial. And then we also used their opacity monitor. What you're going to see is some stock photos and some actual photos. Right here is a stock photo of some opacity here. You go to the next slide, Guisu. This is another stock photo, but generation was really important. Hitting their 100% capacity rate was a goal. This plant had not run really anywhere above 80% for about 3 years. They were mostly restricted by opacity issues that kept them below that threshold. It seemed like when they got above 80%, they had some major opacity spikes. Guisu showed the model of the ESP. It's a relatively undersized electrostatic precipitator for this plant, especially at the higher megawatt loads. So that was a big consideration, was being mindful that we weren't going to exceed the opacity, but trying to see how far we could get, or how close we could get to 100% capacity. The next slide, Guisu, please. So Guisu mentioned you could take to account particle size of the sorbent. That became really important because we were trying to balance, what we'd be getting with mills that would be the permanent installation, and then what we would get with the pre-milled product on site. So we kind of had to balance that. The particle size distribution on the pre-milled product was going to be slightly larger than what we were expecting to see on the actual milled product. And if you see in the center of that photo, this is a real photo, is our silo turned up with its wheels in the air, and our control trailer to the left of that. You go to the next photo, Guisu. So these were actually the physical injection locations we were looking at. This is the pre-SCR location. I actually didn't take a photo of the pre-ESP location because we found out pretty quickly through Guisu's model that was just not going to be feasible to get the removal efficiencies we wanted to. So we really narrowed it down to these two locations, the pre-SCR and the post-SCR. So here's just a location where we were considering doing the trial. You can go to the next one, Guisu. This is the photo of the post-SCR location. This is where we actually did a lot of our injection throughout the trial. We were downstream of the SCR. There were some concerns about injecting upstream of the SCR, and through Guisu's model, we were able to determine that the benefit of injecting pre-SCR was minimal compared to the post-SCR. So we decided to take all risk out during the actual trial and just focus on the post-SCR location. You can go to the next slope.
Hey, Sean, this is Jerry. Just chiming in real quick. I know we kind of hit that 11:35 time, and I know you guys got a couple of slides left, and there's a couple of questions. So if anyone's got to hop off, then hop off and just come check back at the recording. But we'll make sure we get these questions, and we'll just run a few minutes long.
Thanks. I'll try and wrap up, guys. So you go to the next slide, Guisu. This is really the only slide that matters. This is the actual comparison of the CFD model and the actual field trial. During the field trial, we actually noticed the resistivity increased of the flue gas because we were adding sodium bicarb. So the efficiency of the precip actually went up during the trial, which we kind of expected, but we just didn't know how much. So that actually allowed us to increase the capacity past 80%. I think we hit about 100% of their capacity for that unit for the first time for them for a while. I think probably 4 or 5 years that they hit that 100% number without any opacity issues. So you'll see the blue line there is the CFD predicted removal efficiency. And then the red line was the actual trial data. I mean, it was about as textbook as it could be. I like to say that's how they all are, and they're getting there. I can tell these models are just getting better every time we use them. Also, the efficiency for us to focus on just that post-SCR location was huge. It saved the customer a lot of money in terms of time and just us doing some guesswork on site. So it was an excellent tool for us, and we were able to even take it beyond what we had expected because of some other benefits of the sodium bicarb on the conditioning for the precip. So with that, I can't say enough to some of you guys end users to use the CFD to at least eliminate some of the guesswork and really refine, if you are going to do a trial, refine that trial's protocol and test procedures. So I'll wrap it up with that.
Yeah, thanks, Sean. I appreciate it. Thanks, Guisu. And again, I think we do have a couple quick questions. So we just want to make sure we hit you with these guys before we let you go real quick. But there was a question about your case study too, the SO3 with hydrated lime. On the example of like 6 versus the 8 lances, Guisu, did you guys take a look at the comparison of percent removal at different residence time downstream of the injection point? So like 1 second versus 2 seconds, et cetera.
So for this case study, we didn't look at the different injection locations and of course the different residence time and the impact. But certainly the model has the capability to do that, as you can see from the other case studies. But it will be interesting to see how the model, can really answer that specific question. But for this case study, we didn't look into that.
So, but with the model, you could certainly take, the cut from say 1 second, 1.5 seconds, and compare these different.
Yes, that's right. So, in our typical results, we have many curves, like, you have seen like the performance versus, calcium by sulfur ratio, those curve, which is a very typical for further analysis. but we also have a curve of the performance versus the resonance time. So as a a result from the CFD modeling, and with that curve, you can do that kind of analysis, to look at different time and what's the performance would look like.
So, Guisu, on that note, when you guys go to case 3, when you guys looked at 2 lances versus also going further upstream, in that case, did you or could you, I guess, with the CFD modeling, be able to assess if you get a bigger bang for your buck by going from 1 lance to 2 lances versus, just going upstream with, say, 1 lance? Like, we get the question a lot, if I go from 1 second residence time to 2, how much is that going to improve performance? And I understand that, dispersion and residence time, and to a degree, go hand in hand. But is there a way that, did you guys look at that here, or is there a way, I guess, can you speak to that, how to assess what's the right solution, or maybe both, what you did is exactly the right solution, but.
Yeah, in this case study, we looked at both solutions, and we didn't do the cases where we actually, to look at each of the solutions and what's the, consequences, of these solutions. But model, certainly has that capability. But back to this case again, I think the overall performance improvement, although it's not very significant, because the existing performance, it's already good enough in terms of the sodium injected and overall reduction level they are getting. So we are only improving kind of a marginal improvement here by these 2 solutions. So I guess both solutions probably do a little bit on their contribution. But so the model certainly has the capability to, if you are interested in just looking at, what is the contribution from the lenses, and what's the contribution from the time.
And in terms of running those iterations, once you guys have constructed the model, it's a relatively minor expense to be able to run, say, those different iterations. And I think of that from, when someone's looking at going from, say, 1 lance to multiple lances, there's certainly different material handling and equipment modification concerns. So in consideration, so I mean, that just may be a helpful iteration to know that they could run that to see if there's where the diminishing return is.
Absolutely. So in terms of the effort of the CFD model, the most effort is to build, we call it baseline model, which is you're constructing the flue gas duct. A lot of times the flue gas duct, including the ACR air heater, it's very complicated. And once the baseline model is constructed and validated with the existing data, to do more cases, looking at a different the solutions that you're interested in trying to see, it's the effort is much smaller compared to the baseline.
Okay. Well, Guisu, Sean, I appreciate it. This, I think, is super interesting and very relevant. And with that, we're going to wrap it up. And if anyone else, I see we got a handful of you guys that hung on for the extra 10, 15 minutes. I appreciate that. And apologies for running late. And again, I just want to say thank you to our presenters today. Can't do these webinars without having content. I think everything we heard today was super interesting. And thank you to our moderators, as well as the sponsors and the DSUA board, everyone kind of chipping in. So again, stay tuned for the recording. And if you guys are interested for additional content, I know these presentations will go on the archives. The recordings will be available on the website here shortly. If you got something you want to present, submit an abstract, and otherwise just stay tuned for announcements when we get the details on the June webinar all set up. But otherwise, I'll say thank you again for everyone that attended and participated, and we'll catch you next month. Take care, Guisu, Sean, Matthew.